Okay, let's go ahead and get started. Okay, energy spaces. So what is an energy space? Well, basically an energy space was developed to allow people to find solutions to problems that looked something like this. Okay, so the question then is, what is U? And for a long time, it was assumed that they were just classical functions, continuously differentiable, things that you could apply standard integral and differentiable calculus to. But then it turned out that there were a lot of problems where this wasn't the case, and so more generic or general ideas needed to be developed to model these functions. Okay, and so let's define now what we call Hilbert, or more specifically Sobolev spaces. Okay, let's first define what we call L2 spaces. So L2, I guess it can be, it's going to be all those functions W such that when you take W and you square it and then you integrate it, that's a finite value. Okay, and so we call these functions square integrable. Okay, and so this is a Hilbert space. It's actually also a Sobolev space. Okay, so L2 is a very common space. One way to think about it is it's like the space of functions that don't have to be continuous at all. So it includes the discontinuous functions along with a lot of other exotic functions. Okay, now let's define all of the Sobolev spaces. So let's say we're going to use the uppercase H for a Sobolev space, H to the K, where K is going to be a variable. That's going to be all the functions W such that W is an L2 function. W prime is an L2 function. And then W to the K is an L2 function. So one of the things I'm really trying to accomplish is to give engineers an intuition behind what these objects are, because it's one thing to be proving theorems, and it's another thing to be like designing methods and trying to solve problems. And in that setting, the intuition becomes important. Let me ask you this question. Why would we be interested in functions like H to the K, where K is some number of derivatives? Like, can somebody motivate this? Like, why we're so interested in the derivatives being in what we call L2, or they have well-defined integrals? Like, what's the intuition here? Somebody help me out.
Integrable functions have complete metric spaces, so we'll be able to know how close things are together.
Okay, yeah, that's.
I don't know if that's what you're looking for.
But no, it's a true statement. In returning just to the idea of a Hilbert space, it has that structure. My question is, beyond that structure of there being an inner product and a norm and metric and all that, why this? Like, why are we, Sobolev spaces really, they're all about derivatives behaving themselves. Why? Like, remember, this whole field is motivated by trying to solve physical problems. Like we're really trying to develop mathematical models for real problems. Tell me something about functions that model real problems. Like what is the function, what is the function that you've encountered most in terms of using it in your engineering lives?
Well, Mike, in my experience, physics is continuous. Is that what you're aiming at here?
Okay, that you're getting there. Okay, so one word is maybe there's some level of continuity. Okay.
So just
And
so that
I'll put this in print in quotes, because even here, this isn't classical continuity, right? It just means that the derivative, if you integrate it, it's less than infinity, right? It's not that it has to be a continuous function like this. You know, it can look like this now. Okay. So tell me a little bit, anybody else want to add to that, to what Curtis just said?
I was going to say that it's just so that the space in which you're looking to minimize your function, like the solution is defined in there. Like, I don't know, you take, for example, the Dirichlet energy, you know, involving first order derivatives. You want to make sure all of those are integrable. Otherwise, you know, you're going to have infinite values for certain functions.
Okay. Let me, yeah, go ahead. Somebody's going to say something. Sorry to interrupt.
There's a comment in the chat from Enki Luo. She says, or I'm not sure if it's, but they say existence and uniqueness.
Okay. But what I'm after, guys, I'm after intuition. That's the most valuable thing that you have. Intuition.
My intuition's always guided by the equations of motion.
Okay.
And I suppose I would say that if you control derivatives, you can then control like the energy.
There you go, Greg. That's the kernel of this whole thing, right? What Ryan said is right. You want things with finite energy, right? That's a basic prerequisite. But it's in the derivatives that you find the energy in systems, right? It's the way that the derivatives behave, how fast they blow up, how smooth they are, et cetera, et cetera. So there's a reason that these are called energy spaces. It's because the natural functions that model things in nature, first of all, they have to be in some sense bounded. The energy has to be finite. And you have to have some control over the energy of the derivatives. Okay, so the word that I would use is the energy in the derivatives. And so this is a really critical idea that really, if you develop a strong intuition about this, these spaces begin to become less mysterious as far as why we're using them. Okay, so notice also that now when we are saying a derivative, W prime, no longer does W prime have to be in some, you know, C1 space, like space of continuously differentiable functions. It's an L2, which means that the derivative, right, if we were to look at, we're just saying that W prime integrated has to be less than infinity. And now all of a sudden, this idea of a derivative becomes much more general. And we'll actually call these generalized derivatives. And as we talked about yesterday on Monday, what was discovered is that a lot of these integral equations, you can't actually find their solutions in the classical CK spaces. And so HK spaces were developed, which have more functions in them, and they're more general, the derivative behavior. So a nice intuition here, one that I think about is, and let me ask this in the form of a question. How are the CK and the HK spaces like related to each other? Just at a high level, just an intuitive, not looking for a theorem. There are theorems that, of course, answer this question, but just because you can restate the theorem doesn't mean that you know what it means. Okay, so how are these guys related?
It seems like CK is a subset or subspace of HK. And from your notes, it said that there were additional functions that aren't as strongly differentiable in
Exactly. Yeah, so CK is contained in HK, and it has a whole bunch of other functions that are like almost CK, except at some isolated points, okay? And so it's essentially, there's this very close relationship between the classical differentiable spaces, the CK spaces, and then these more generic energy spaces. And so when we get to finite elements, what you'll notice is that we often are working in here in order to approximate functions in here. And the reason we do that is because there is this very close relationship between these spaces. Okay, let me scroll.
Dr. Scott,
Yep.
can you help me? I have a question on what you just stated there. So why would we want to approximate those additional functions in HK just to help with the intuition? What's their importance with finite elements? Because we're working in CK because we can, but then we want to get these additional functions from HK.
Well, yeah, in finite elements, it's all about computing functions that are, you want to deal with functions that are easy to compute. And so that's why we tend to work in CK, because it's very easy to generate a space of CK functions for a very generic geometry. And we also know that an infinite sequence of, you can approximate any function with enough polynomials.
Right.
And so that's kind of the idea, right? And so you just generate these larger and larger polynomial spaces, and you begin to be able to approximate very well functions in these more general Sobolev spaces. So we don't really know how necessarily to discretize directly HK, right? But we do understand how to discretize what we call splines, right? In the context of a spline method, like the finite element method.
Mike, can I ask a question?
Or did I miss it?
So I understand that we can work in CK space and we can approximate HK, but I guess application-wise, what are those functions in HK either look like, or I guess why do we want to approximate those certain functions in HK when we can?
Oh yeah, it's because boundary value problems, their solutions live in the H spaces.
That's right.
That's the fundamental thing, is that's where the boundary value problem solutions naturally live, is in the Sobolev spaces.
It's like a step function or a delta function would be a good example.
Yep.
Right.
Yeah.
Thank you.
That's how you tie that back to that. It's just the mathematics has indicated, as they've studied boundary value problems, that these solutions, they live in these more generic spaces. And so analytically, it's nice to know that, but then from a numerical point of view, we don't really know how to discretize HK directly, and so we do it by means of polynomials, usually speaking. Does that answer your question, Ian?
Yes, sir. Thank you.
Okay.
Mike, can I ask a question as well?
Sure.
So can you give, when you say CK is classically differentiable, can you remind me exactly what that means? I mean, I mostly know what it means, but like exactly. And then can you provide an example from physics that's intuitive about how the solution is not in the CK space, it's strictly in the HK space, so that we kind of have a strong intuition about what you really mean by this.
Okay, yeah, so a C, let's say a C1 function. So if we have some f in C1, and it's defined over, let's say, some domain omega. So f at x, let's say to the left of, right, like within some epsilon ball of x has to be equal to f x to the right, right? So we're basically looking at limits converging from the left and to the right. So if this is the first condition, this is sufficient to be in C0, right? It's a C0 function if this holds for all x in omega. Is that okay, Curtis? Do you see what that means?
Yep, following that. Mm-hmm.
And then f prime x to the right, this is C1. Okay, so to be a C1 function, you have to be a C0 function, and you have to have this second condition on the derivatives. And so if this holds, we say that this function is continuously differentiable. Okay, and then this just keeps going down, C to the K. All right, so that's what we mean by these classical continuous spaces are these kinds of spaces where you're taking go to a point X and you look at the limits coming from the left and to the right, and if they're unique and the same, then you have on all the derivatives up to the kth derivative, then you're in CK. Okay, then what was the second part of your question?
I want to know, I was hoping you could provide a physics example where it's obvious that the solution is strictly HK but not CK. So that way I can understand the limits of our CK approximations.
Right. Let's see. Let's see. That's a good question. An example of
a point load on a beam.
Yes, Kyle, that's a good one.
So like a wire instead of
you have a beam. Let's say you have a beam, and you have some load P at a point, right? So the solution to this is not a classically differentiable function. Because you're essentially applying a load at a single discrete point.
So you're saying that this is not a C, but it is within H?
That's correct.
So would a more intuitive example be the wave equation for a wire, because your slope is clearly discontinuous since you have no bending resistance? You know what I mean? Like the deformation's shaped like a wire, like a triangle.
Well, yeah, so the absolute value function is also not a CK function. For me, coming from structures, this is a very simple example here of a function that's not a CK function. A point load on a structure.
But the function that you're talking about is the function of the load on the structure, the forces within the beam?
Of the displacement. So if you were to compute the displacement of this guy,
okay,
as a function of x, this guy would not be in a CK space.
Well, C1.
It'd be in C0, right?
Mm-hmm.
Would not be in C1.
But it would be in H1.
Yep. Okay. Yep. So there's an example. Yeah, I mean, that's a good question. I think I'm going to add that to my notes. Maybe I'll just work this problem and then we can Let's see what it is.
Maybe if you
Um,
use like Green's functions to come up with solutions to a problem before, like if you apply the differential operator to the Green's function, then you get a delta function.
Yep, that's another classic way of coming up with analytic solutions to these guys. And what you'll find is that these methods will produce a lot of non-CK functions. Is that okay, Curtis?
Yeah, I'm following what you're saying and I'm still digesting it. Yeah, thank
Okay.
you.
So let's talk about what we mean by these derivatives, right? Like the derivatives being in L2. We call these weak derivatives. And again, it's important to have some intuition to guide you here. So what I want to do is give you an example, and I work an example in the course notes that I'll repeat here. Let's look at the absolute value function x on omega equal -1 to 1. Okay, so the graph, the function looks like this. And then we want to show that this guy is not in C1. So it's not going to be in C1, but then we're going to show that it actually is in H1, meaning it doesn't have a classical first derivative, but it has a generalized first derivative. And this will help you see exactly what we mean by a weak derivative. Okay, so let me clear this here. Okay, so here we go. So so if you have U and V, and again, for you engineers who are thinking this is way more math than you wanted, this isn't the whole course. So I just want to reiterate that I just have learned over the years it's better to just eat your vegetables first, and then we'll enjoy the dessert after. So I'm going to try and go through the math, and then what you'll be able to do is you'll be able to return to these concepts again and again throughout the course, and we'll continue to strengthen them. Okay, so if U and V are integrable, let's say on AB, what we say is that we say V is a weak derivative of U if the integral from AB U phi prime dx is equal to the negative dx for all phi in C infinity phi at A equal phi at B equal to 0. Okay, so this is the definition, and it's not there. It's not. I'm not completely rigorous here, but it's enough for you to see what's going on here. So if you want to know what the weak derivative of U is, the way that you compute it or determine what it is you take U and we say you test it. And that means you integrate U against all phi in C infinity. These are like little bumps throughout the domain, right? There's 0 on the endpoints, and then there are all these little C infinity bumps, smooth bumps that you can test U against. And essentially what phi is doing is it's it's basically filtering out for you the information about u. So we're reconstructing the function u by testing it against a whole bunch of infinitely differentiable functions. And so because phi is infinitely differentiable, we can take its derivative. Notice there's no derivative on u, and u is integrable, so this integral is fine. And then what we do is we do integration by parts. So this right here is integration by parts. And all of a sudden, what we can do is we can pass the derivative off of phi and compute what v is under the integral. And then since this holds for every single, an infinite number of test functions, we've actually reconstructed the derivative, the weak derivative of u. So do you notice that v, it is only defined under integration. It never stands alone, right? This isn't a point-wise statement. You don't say anything about v in a point-wise sense. All you're saying is that under the derivative, under the integral associated with a bunch of test functions, this is what this guy looks like. And so let's do an example for the absolute value so that you can see what I'm talking about. All right, so let's look at u equal to the absolute value of x on -1 to 1, okay? So let's take this derivative now. So, or this integral, we got -1 to 1 u phi prime dx. Okay, this integral is well defined. Now let's do integration by parts. Let's first insert the definition of the absolute value into u, which gives us -1 to 0 of minus x phi prime dx plus 0 to 1 x phi prime dx. Now we do integration by parts on each of these integrals, right? So we're going to pass the derivative off of this guy onto this function. Now this function is now differentiable on -1 to 0, right? Notice how we have, in some sense, we've cut out the point 0 in this integral in some sense, right? And that's an important property of the integration process. So if we do integration by parts, we end up with -1 to 0, -1 phi dx minus 0 to 1 phi dx. Okay, and so now we're done. This defines a function, right? So this is our v, -1 to 1 v phi dx, where in this case v is equal to -1 if we have -1 less than or equal to x less than 0, and then 1 Okay, so this function v clearly is not a C1 function, right? I mean, u is clearly not a C1 function, so it doesn't have a classical first derivative, but it does have a weak derivative, and the weak derivative is the function, it's just the classic step function, right? So it's -1 plus 1. And so this function v here, because it does have a weak derivative, therefore its derivative is in L2, and so it's in H1. So this guy is in H1. Okay, so this is really important. Like, this is just, from my perspective, it's just, you just have to know this in order to do the engineering in physics that follows, because like this is the whole foundation of where we look for solutions and why we look for them there and what their properties are.
Is this an
Go ahead.
question?
Yep.
Is this in H1 because they meet at 0, or if they didn't meet at 0, would it still be in H1?
So what this means, the way that to interpret this is that this function, do you see how close is this function to being C1? Can somebody tell me?
It's made up of 2 C1 functions.
Yeah. So it's C1 except at 0, right?
Yeah.
And so the integration procedure, it's called Lebesgue integration. What it allows you to do is integrate functions everywhere except at what we call a set of measure 0, which is just like a whole bunch of points. You can basically ignore those. The integral cannot differentiate between two functions that are only different in a set of measure 0, right? So what the integral is allowing us to do is to basically analyze functions that don't have the classic idea of differentiability through the properties of integration. And so this function, again, remember that I said there's this nice kind of conceptual linking between the CK and the HK spaces. This tells you, this kind of helps you see how close they are, right? So this function is in H1, not in C1, but boy, it's really close to being C1. It's just not C1 on a set of measure 0. So this is the important, like the important point here. And there are a lot of solutions to problems that are going to look like the absolute value function, right? Or have those kinds of discontinuities at certain points. Okay.
Just a clarification, V is not in H1, like you wrote down there, but U is, that's what you're trying.
Yeah. V is just its derivative. U, so what we've shown is that U prime is equal to V, and it's actually in L2. That's the right way to say that. So U prime is in L2, U itself is in H1. Okay, any more questions on that? Yeah, and in the context of splines, using splines, the whole business is building these function spaces, right? So this information, which if you just use linear finite elements, like some people don't ever know anything about this because they're essentially have only one way of doing approximation with the linear functions. With splines, we have this huge new, like this whole frontier of spaces. And so understanding this information becomes critical. Okay, so let's talk about now just some properties of the Sobolev spaces. I've already said that CK is contained in HK. We also have that HK plus 1 is contained in HK. Okay, so there's less functions, right, in these higher K spaces than there are in the lower K HK spaces. And now the question is, we have this, notice that we can say that CK is an HK, but now the question becomes, when is HK contained in some CR space for some R? Let's say R not equal to K. So here's a question. And what does your intuition tell you here? Like, if CK is really, really, really close to HK in some sense, then what do we think about CK minus 1? What's its relationship to HK? What would you think?
Would it be HK minus 1?
What's the relationship, for example, to between HK and not CK, but CK to the minus 1. Right, so this guy is like that, right?
That HK should always exist for CK to the minus 1.
This is what your intuition would kind of guide you to say, right? Well, if HK is really close to CK and CK to the minus 1 is bigger than CK, maybe we have hope that HK is actually in CK to the minus 1, right? So maybe H1 functions are actually C0 functions. That seems reasonable, right? Notice that the absolute value function, is it a C0 function?
Yes.
It is a C0 function. So at least for one function, we know that this is true. And so this is a very, very important idea. And it's made precise through what are called the Sobolev embedding theorems. And it's really answering this question of, how big of a CK space do I need in order for an HK space to live inside of it? That's essentially what it's trying to, the question that it's trying to answer. Why would this be why would this be an interesting question from the standpoint of finite elements? How many of you
find everything under CK, under some K, some CK, right? If it's high enough.
Yeah. I mean, how many of you, we have a lot of people working in the labs who have written papers. How many of you have described a method where you said something like, I'm going to look for a solution in H1, and I'm going to test it against delta U's in H1. Anybody ever written this in a paper? And then you describe your method? And then what kind of finite elements do you use in order to find the solution? What space are they usually in? Classical finite elements.
C0.
C0 functions, right? This is the classic FEA space. Okay, and the vast majority of problems in structural mechanics, they only require one weak derivative. So they all live in H1. And so this is the motivation for why C0 finite element spaces are so nice. Because if we were looking at infinite dimension spaces, so we had an infinite number of C0 functions and an infinite number of H1 functions, we'd actually know this in 1D. So you should be able to compute it exactly if you had an infinite precision machine. Okay, and so the Sobolev embedding theorem says if omega is an open set in R to the n, and S is greater than n over 2 plus k is really the floor, then H to the S is in CK, and B, this just means bounded. It's just a technicality. All polynomials are bounded, but anyway, all the bounded CKs. So if we're in R1, if n is equal to 1, what do we know from this formula? It's a quiet group.
So I'm just having trouble. Where does the n come into play? Is that just any integer?
Yeah, so n here is the dimension of the space. R1, R2, R3, R4, R5, right? These are the classic vectors that you will have worked with, you know. N is the dimension. One dimensional, two dimensional.
Okay.
Okay, so if n is equal to 1, then what does this look like? Well, s better be greater than 0 plus k. So H1 is in C0, right? H2 is in C1, and so on. And then if n, let's say if n is equal to 2, then this becomes 1. So then this one doesn't work. Then this goes to C0. Then H3 is in C1. Do you see the pattern? So for higher dimensions, there's basically for higher dimensions, there's more and more chance that your functions, your H functions, your Sobolev functions can be really weird, right? So like in 1D, there's not a lot of chance that things can go haywire, but in 2 and 3D, things can get really weird. You can construct really strange functions. And so the embedding becomes weaker and weaker. How's everybody doing? This is the thing about these Zoom meetings. I can't tell. I have no idea how you're doing.
In terms of the nomenclature that you're using, the R, we've used that for real numbers. What are you using it for this time?
This guy.
R to the end.
Yeah, this is real numbers. Real numbers. So these are, so if n is equal to 1, that's just the real line, right? R. If we have R2, then it's like everything on the page, right? X,
Okay.
Y, that's R2.
So often in this case containing vectors.
Yep, just vectors. X, Y, Z is R3. Right, so it's like geometries in, so in R3, it's like all geometries in the physical world, right? We live in R3. Is that okay?
Yep.
Good. Any other questions?
So with this formula, we're faced with a problem, a physics problem to analyze, and we have HK problems, and we want to fit them into some sort of CK space so that we can actually make the calculations, right?
That's exactly right. Yep.
Okay.
So before you even pick a finite element mesh or a discretization, the very first question that you should answer is, what Sobolev space does my solution, should it live in? Like if I look at the integral statement that I'm trying to solve, where is the natural place? What is the HK space? And then that should tell you the minimum CK space, right?
Right.
But remember, there's a caveat here that the Sobolev spaces are infinite dimensional. So to get an exact representation in a CK space, you would need an infinite number of those functions. In finite elements, we have a finite dimensional space. And so in that sense, it doesn't really matter whether we do C0, C1, C2, because it's just going to be about how many of those we have, right? But it should tell you, like, if you have an H1, if you have an H1 space, like a C0 finite element mesh is a reasonable place to begin. Although we'll find in finite dimensions, it may actually be better to do C1 or C2.
So the K value we're getting is the minimum we need.
Yeah. Yeah.
Okay. But higher order are going to be possibly more accurate.
That's right. For a given number of functions that we have, there may be reasons to use more functions that are smoother.
Smooth means higher K.
Yep.
Okay.
Okay, so this is like the whole foundation of numerical methods, like the finite element method. This is like this is really a much more powerful way to think about what we're doing than maybe just thinking about nodal finite elements and so for the engineers who are taking this class, and especially if you're doing it for credit, it's not something to get discouraged about. I have no expectation that you're going to have a really nice understanding of these concepts in the first week of the class. But as the class progresses and we do practical problems in the context of these mathematical ideas, you'll be able to return to them again and again. And these concepts will become very practical to you over time. And that's a much stronger foundation. And really for spline-based finite elements, it's the only way to go. It's the only way to really understand, have enough understanding of the methods to make any progress. And so if you're doing the homework and you have really struggling, that's fine. We'll just keep coming back to this, and over time you'll develop that skill set. I'm going to have a mathematical preliminaries 1, which is what we're going through now. Then later in the course, I'm going to probably have a mathematical preliminaries 2, which is going to be all the tensor and vector calculus. So that will be important for continuum mechanics. But this is really the foundation for the next little while.